All right, so what do I have drawn up here? Our favorite molecule of the day. Any of you recognize this?
Glucose.
Thank you. Glucose, right? 6 carbons in a line, and we have our carbonyl group at the top, right? You guys recognize that? And you also know that glucose can do that funky thing where it goes from being a straight line molecule to flipping into a ring, right? And it flops back and forth between those two shapes. This is going to challenge my drawing ability. All right. So glucose can flip back and forth between these two arrangements, correct? Yes? All right. Okay. So what our lab today is going to learn, is how you can do chemical tests to determine what kinds of molecules are floating around in a solution. So here's a bottle with no label on. What's in here? Who knows, right? But we're going to learn a test, or a bunch of tests, that you can do on whatever this solution is in this bottle that will tell you whether there is sugars in here, whether there is protein in here, what could possibly be in here. The first test you're going to learn is the Benedict's test. And the Benedict's test is a test that detects the presence of monosaccharides. So can someone tell me in normal words what a monosaccharide is? Go ahead.
It's a monomer of glucose.
It's a monomer, right? It's not a monomer of glucose because glucose is a monosaccharide, right? So a monosaccharide is a simple one sugar. So glucose is an example. This is an example of a monosaccharide right here. It's just a single glucose molecule. Right? It's not hooked together with other molecules to make a chain yet. It's a simple sugar. All right, so to test whether this has any monosaccharide in it, for example, glucose, we're going to use a chemical called Benedict's solution. You'll have some on your benches, and it looks like this. It's a beautiful blue color. And the reason it's blue is that it has floating around in this solution copper ions. This is copper. And when it's an ion, when it's lost a couple of electrons, it turns into a copper 2+ ion. And copper 2+ ions are this pretty blue color. So in this bottle right now, I have a ton of copper ions, 2+ ions floating around. Now, if I were to take my solution, let's say it actually has glucose in. So this is a solution of glucose. This molecule right here is in this bottle. And I were to mix it with my copper-containing Benedict's. All right, here's what happens. This copper ion can go in and attack this double bond. Only this double bond, this carbonyl group up here. And this carbonyl group, there's a double bond, there's a covalent bond here, 2 electrons, and a covalent bond here, 2 electrons. So there's 4 electrons up there between that C and that O atom. This copper ion is going to swoop in here, and it's going to grab one of those electrons, break that bond. And we're going to take an electron from that bond. There it goes, E-. And this copper is going to take that electron. If we add an electron to this copper, it changes from being 2 positive to now only being 1 positive because we've added a negative thing in here. So we brought the charge down from 2+ to 1+. And it just so happens that copper in its 1+ state is red. So copper 2+ is blue, copper 1+ is red. So if I was to mix my blue copper 2+ containing Benedict's with my mystery solution, and it goes from blue to red, that tells me that in here there is a molecule, a monosaccharide molecule that has a carbonyl group that's giving the electron to the copper to make it go from blue to red. Make sense? If this stays blue, what does it tell me is in here? Or at least what does it tell me isn't in here? There's no monosaccharide in here. There could be all kinds of other things. Who knows? Protein, starch, who knows what else could be in here, but definitely not a monosaccharide. All right, good. So that's the first part. That's pretty straightforward. Everyone good with that? All right. Next up, we're going to get a little more complicated. So my sugar, my monosaccharide, can flip itself into a ring and back and forth, right? I can take two of these rings side by side and hook them together. So if I take another one, I do that reaction that we've learned, dehydration synthesis, and I can turn it into, all right, what did I draw here? What can you call this?
Disaccharide.
A disaccharide, excellent, because it's two sugars stuck together now. All right, this is actually a maltose. Two glucoses stuck together make maltose, but a disaccharide is fine. Monosaccharide, disaccharide. Okay, when the sugar is in its ring, does it have a carbonyl group? Yes or no? No double bonds here, right? No carbonyl groups. And as soon as we hook two rings together, they cannot unring themselves. They're stuck like a ring now because they're hooked together. So this is a disaccharide. So let's say, let me just grab. This is a bottle that's got sucrose in. This is a disaccharide. All right. If I were to mix my copper-containing Benedicts with my disaccharide, is this going to turn from blue to red?
No.
No. Why not?
No carbonyl.
Because there's no double bond, there's no carbonyl group. Now you might look at this and say, look, there's glucose right there. And glucose turns this from blue to red. So why won't this? Well, it's not glucose anymore, right? It's now, it looks like it's glucose, but it's glucose as part of a bigger molecule. This is now maltose. It's something new and different. And it doesn't have the same chemical properties of each individual ring on its own because they're put together as a giant bigger molecule. So this is maltose or a disaccharide, no double bond, will not turn this from blue to red. This stays blue. Okay, make sense? All right, let's do another step. There's more. All right, got my disaccharide. Maltose, sucrose, whatever it is, it's a disaccharide. This one is maltose. I'm going to add in some acid, like your stomach. I'm going to add in some water, like your stomach. And I'm going to do a chemical reaction, and we're going to separate these. So I took my disaccharide, I mixed it with acid and water, heated it up a bit, separated these two apart. Now I'm going to take this and pour this over here. Will it change color now? Yes. Why do you think so? Because I broke it down back into, in this case it's glucose, but more generically, monosaccharides. All right? And even though I drew them like rings, what can these rings do? They can open up now because they're just single monosaccharides, and they can flip open and recreate their double bond. Do you remember what we call this reaction where I split something using water? Excellent. This is hydrolysis, right? So if I take my disaccharide, whatever it is, sucrose, maltose, lactose, my disaccharide, do hydrolysis first, and then test it, then it's going to give me a positive Benedict's result. It'll turn from blue to red. But if I don't do this and just test this molecule, it won't turn red because I've not got a monosaccharide here, excuse me. All right? Makes sense? So one last little bit of chemistry. Pick this up. In your lab, pre-lab, it had a special name for these monosaccharides. Do you remember what it called them? A new term we haven't used before?
Reducing sugar.
A reducing sugar, yeah. It called these reducing sugars. All right. So this is a strange name. We've never heard of this before. So reducing sugars, this is referring to a process in chemistry that's called reduction oxidation. That's a mouthful. So the long term is reduction oxidation. That's a lot to say and a lot to write. So instead, we just say redox. Redox reactions. Redox reactions are very common in chemistry and they're super common in biology. We do lots of things that happen in your body are redox reactions. Now, what are redox reactions? They are to do with electrons being moved from molecule to molecule. They're nothing to do with reduction in size or getting smaller or shrinking, and it's nothing to do with oxygen. So the name isn't really very helpful. Don't think about size, don't think about oxygen. What you're thinking about is electrons. Now, when something gains electrons, we say it's been reduced. And when something loses electrons, we say it's been oxidized. Now, blah, 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 blah. I'm sure that just went in one ear and out the other. So to remember that, we use a little acronym or mnemonic, and we say that Leo, the lion, says grrr. Right? He growls. Leo the lion says grrr. So that's loss of electrons is oxidation, and gain of electrons is reduction. This is the only way I can remember. I'm sure there's other ways. Maybe you're got a better way of remembering it than I have, but this has worked for me for like 30 years, so I'm sticking with it. So let's look at our picture here. My glucose molecule, when the copper came in and did its thing and went from blue to red, the copper ion, did my glucose molecule gain electrons or lose electrons?
Lose.
It lost an electron, right? Because that double bond was broken and the electron went to copper. So the sugar, the glucose, lost the electron. Loss of electrons, it was oxidized. The sugar got oxidized. What happened to the copper? Did it lose an electron or did it gain an electron? It gained the electron because it went from 2 plus to 1 plus. So the copper gained electrons, it was reduced. Okay, so the sugar was oxidized, the copper was reduced. We call this a reducing sugar because it is able to go about reducing things. It's the agent of reduction. All right, it doesn't itself get reduced, it gets oxidized, but it's causing something else to be reduced. So let's say I'm glucose, all right, and Ivan is copper. Here I am with my electron in my double bond. I just got oxidized because I lost my electron. He just got reduced because he gained the electron. I reduced him. I'm reducing him, right, by giving him an electron. So I'm a reducing sugar. And that's where that term comes from. That's why we call monosaccharides reducing sugars, because they're able to go around reducing things by giving them an electron from their carbonyl group. Okay? And that works for any monosaccharide, not just glucose. We call all these monosaccharides reducing sugars. There was an example in your pre-lab. It was ribose, I think, reducing sugar. It's able to give an electron to copper to turn it from blue to red. All right? So we've covered the chemistry of the Benedict's test, which is all this, the oxidation reduction terminology, and we also covered this simple condensation synthesis, hydrolysis process, and which of these will give a positive Benedict's test and which of these will not, due to whether they have a carbonyl group or not, depending on their molecular shape, structure.